So as promised, I want to tell you about this do notation, which makes writing code with monads much nicer in many cases. So as an example, let's suppose we have this task. We want to write a program that prompts the user for a number, and then prompts them for a string, and then prints out their string n times. Obviously this is not super interesting or realistic, but it'll be a nice small example to see how do notation works. So let's just first see if we can write this just kind of directly using what we know, and then we're going to go through a series of transformations where we make it kind of nicer step by step, and then you can see kind of where the do notation came from historically. So let's we'll call it prompt and repeat, or we'll call it prompt. I'll just call it copy prompt. Sure. So this is going to have type IO unit, because ultimately it's going to do a bunch of IO, but it's not going to return anything. So how do we do this? Well, first we say put string please enter a number, and let's see, and then we will wait for them to type something, so we'll call get line, and then we need to do bind because we need to take the output of get line and do something with it. So I'll just call this S1. I'm going to have a lambda here. And then what do I want to do in here? I want to have another IO computation that's going to, well, it's going to put str again. Please enter a string. And then I'm going to say we'll get line again. And we'll call this S2. All right, this is all still inside this first lambda to this get line. And then now this is inside this lambda to this get line. And finally, I'm going to say, let's see. So there is a function called replicate m. I think we want replicate m underscore. So replicate m underscore, let's see. I need to import control.monad to get replicate m underscore. And let me just show you quickly what replicate m underscore does. So you can actually see its type here. So it says, well, it works for any applicative actually. And it takes a number and a computation of type MA, and it returns an M unit. So basically what it does is it does this computation, n times, and composes them all together. The underscore means it's going to ignore the output values and just give us a unit. Right? There's also replicate M without an underscore that collects up the all the A's that get returned into a single thing. And I think you could figure out how to implement this using things like traverse or the sequence function that we did the other day, together with the function replicate that just replicates a list. So you can think about replicating this a bunch of times. We get a list of MA, and then we do the sequence operation to get a M of list A. Okay, so I want to replicate it read S1 times. Again, we'll just assume that they typed in a valid number. It'll crash if they didn't, so that's okay. And the thing we want to do that many times is put strlen S2. Okay, so let's try this out. I am very aware that it is extremely ugly, and that's the point. So copy prompt, please enter a number, 5, string hello, prints it 5 times. Okay, so it works, but it's really ugly. I mean, it goes all the way off the end of the line, it wraps around, it's got like nested stuff. So let's make it better. So one thing I can do, right, is that actually Haskell is pretty lax about being able to break things over multiple lines. You don't even have to, it's like in some languages you need to put like a backslash at the end of the line or something to continue onto the next line. in Haskell, as long as the indentation, right, the indentation is really what's telling it when you're starting a new expression. And so we can just put things on lines however we want. So I'm going to put some things on separate lines. So we'll put this down here, get line, and then, I don't know, we'll do, let's see, I want that moved over a little bit. And, well, something like, okay, looks a little ugly still. We'll make it even better. Right, but so now, I mean, at least we put things on different lines, and we can see there's still like some nesting, some like multiple nesting going on. Like this is nested inside of this, which is nested inside of, and like some indentation. And you can imagine if we needed to do a lot of these things in a sequence, it would like kind of march across the page to the right, and that would still be pretty ugly. But we can just make sure that it still works. 5, hello, okay, that still works. So the other thing that, and I think maybe we've seen this before, a couple things. Number one, we can make use of the fact that like this and-then operator and the bind operator are chosen to have the same precedence level. So if I say, info on this, it has precedence level 4, and it associates to the left. And if I say info on bind, okay, so actually, I was expecting it to have the same, but I guess that has lower precedence, which means, yeah, it still works because this bind is always followed by a lambda, and the lambda is going to sort of serve to group everything together, even if it's got and then operators in it. So the point is that we can, I actually don't need these parentheses here, right? Because this whole thing is just, the second argument to the bind is just this lambda, which is this followed by everything after it. And then likewise, I don't need this. So in fact, I don't really need it to be indented at all. Because every time I have a lambda, it extends all the way to the end of everything else. And so having it indented is kind of pointless because it's simply going to, like, everything after it is going to be indented, and there's going to be nothing that's not indented afterwards. So so this is looking better. Let's try it. Okay, still works. And for a while, when people first introduced the monad instance for I/O, and this is how people would do I/O, and I/O is kind of the original motivating example for this, or one of the original motivating examples, but there were others as well. And of course, they were using this operator, but I mean they're equivalent, right? So we could use this one, which is defined for any monad. And you notice, like, if you squint at this, right, it really looks like each line here is sort of like a line in an imperative program. It says do this, then do this, then do this, then do this, then do this. Right. One difference between some of these lines is that some of them, right, we are followed by one of these and then operators, and so it just says do something and it doesn't produce a result. Some of them produce a result that we care about, and so we're using the bind operator instead of this and then operator. And then we have a lambda that gives a name to whatever the output of this thing, and we get to use it anywhere we want in the rest of the expression. And so this kind of style is so common that someone said, you know what, it would be nice if we just made some special syntax for that. Okay, and this is called the do notation. So the way do notation works is you first write do, and then the indentation level of the very next thing after do determines the indentation level for the whole thing. So anything that's indented that much is part of the do block. And then if the first thing that's indented less is no longer part of the do block. Okay? And basically, so these and then operators, we just get rid of them, because do notation says if you just have something by itself on a line, then it just assumes you want to sequence it using and then to ignore its output and then go on and do the next thing. And then these things here, we just flip them around with a little left pointing arrow, right? But it means the same thing. So up here with the bind, it meant do this thing and take its output and call its output, you know, S2 in this case, and then we get to use S2 in the rest. This means the same thing. This says, you know, run getLine and then take its output and call it S1, and then we can use S1 in the rest. But in particular, it really does mean we're going to call bind. So like this do notation just turns into, it desugars to this using bind operators. So if you want to understand what this does, right, this is not just, well, okay, let's hang on before I get to that. Let's just test this and make sure it still works. Copy prompt for 5. Hello, that works. Okay. So backing up a little bit, with I/O, with the I/O monad, right? This really is exactly like, you know, an imperative program, and so this little left-pointing arrow means assignment, right? It says assign the output of getLine to S1. Now, of course, for other monads, bind does different things, right? So, for example, if we use the list monad, so for example, let's make a function to find Pythagorean triples. And we're going to do it using do notation. So first I'm going to say, so this is the list from 1 to 100, and I'm going to put a left arrow in A. And so really that turns into a call to bind. And when I do a list and then bind, and then I say lambda A something, right, it basically means I'm going to take that function and run it once for every possible value in the list, right, because it sort of represents non-determinism. So if I to say like B is going to go from, you know, 1 to 100, C is from 1 to 100, and then we'll say something like, you know, if A squared plus B squared equals C squared, then we're going to just have the list containing this triple ABC, else empty list. But basically this really is acting like 3 nested loops, right? So for each one of these things, it's going to call the rest of it once for every possible value. So, or you could also think of it as saying, you know, pick A non-deterministically from 1 to 100, pick B, pick C, right? And then for every possible combination of values, right, we're either going to produce a single triple or we're going to produce an empty list. But then because of the way the list monad works, right, all those possibilities are all going to get kind of put into one giant list. And so if we run this, it takes a little while, but eventually we get a list of all the Pythagorean triples, you know, less than 100. And you could do the same thing for, you know, maybe. So for example, well, I don't have a good example off the top of my head, but every time you do this kind of left arrow thing in a do notation, if it's for maybe, it means that, you know, the thing over here could possibly return a nothing, or it could return a just. And if any one of these things gives you a nothing, the whole thing is just going to stop, right? But otherwise, if it gives you a just, like, you know, in this case, A would refer to that value that was inside the just, and you can keep going with it. You can also do this for parsers. Maybe we'll see an example of that later. There's all kinds of things that you can use this do notation with. And it's a very nice convenience to be able to use that. So another way to think of this is, right, do notation really looks like an imperative program, except that by picking an appropriate monad instance, you get to kind of decide what semicolon means. So sometimes people talk about monad being a programmable semicolon. So a semicolon in the sense of a language like Java or C that has a semicolon at the end of each statement. a semicolon that separates one statement from the next statement. But here we get to decide, what does that mean when you do to compose two statements? Does it just mean do this, then do this, or does it mean something with non-determinism or potential failure? We can kind of decide what it means.